Hello, everyone. I am Udita Mukherjee. I am a PhD candidate at Tulane University working with Kyle Straub. And this is a chapter from my PhD thesis titled Field Testing Storage Thresholds for Environmental Signals from the Mississippi Delta. I would like to thank the organizers and the chairs of this session for giving me an opportunity to talk about my research, and also to the funding sources for help with this project. So as we all know, sediments are transported from the source terrains to sedimentary sinks, and these sediments carry environmental signals with them. However, these signals may or may not be preserved in the strata. And the fidelity of the stratigraphic record can be reduced due to a number of reasons, including buffering or diffusion of signals, due to incompleteness of the stratigraphic record. But what we are really interested in is understanding how the fidelity of the stratigraphic record can be reduced due to shedding of signals due to autogenics. Here we are seeing a rice pile experiment, and this is a steady input, but the output that's coming out is unsteady. And due to the storage and release of sediment, in this case, rice grains, the signals are lost at the output. These signals are getting smeared in space and time. And even if we had enough data in the output, we could not have reconstructed them. And a number of numerical physical experiments have been conducted to construct the signal shredding theory. Also, relative sea level signals can be shredded at the sink. This is an experiment that was done by Lee et al. 2016 in the Tulane Delta Basin, where we see construction of channels and a change in the RSL signal at the sink. There's a stratigraphy that was created from this experiment, and when the mean depositional rate was calculated and the imposed periodicity was calculated, it was seen for small enough attributes of the RSL cycle. The RSL signal may not be found, are not found at the sink. So this is our first foray into field testing the signal shredding theory. And before I go into the nitty-gritties of the project, I would like to introduce two non-dimensional numbers that we use to calculate the storage potential, basically. And those are the non-dimensional length scale, or H star, which is basically the range of the RSL cycle divided by the deepest channel, deepest depth of the channel, which is HC. And T star, which is the time period of the RSL cycle divided by the compensational time scale, which basically tells us what is the time taken by a single grain of sediment to actually go below the reworking zone. And if H star and T star are both less than 1, then they're shredded. And if H star and T star are greater than 1, or if both are greater than 1 or 1 is greater than 1, then the RSL signal is preserved in the strata. And here we show that for a Mississippi scale system with Miocene sea level changes, it would have been shredded, whereas for a quaternary sea level change with a Mississippi scale system, it would have been preserved. We also hypothesize for like different values of H star and T star. We'll see different signals, different expressions in the strata. So for H star greater than 1, but T star less than 1, we should see thicker sand bodies. Alternatively, for H star greater than 1 and T star less than 1, we should see wider sand bodies and mass balance fluctuations from proximal to distal. But for both H star and T star greater than 1, we should see thicker and wider sand bodies and the mass balance fluctuations proximal to distal. And please keep this in mind because I'll bring this up later in my talk. Of course, for H star and T star both less than 0, there should be no RSL signal preserved. So the goals of the projects are, this is the first field testing of the signal shredding theory. Also, we are trying to understand how much effect does the smaller coastal systems have in the stratigraphic architecture of a large sedimentary basin compared to the trunk system. And for for this, basically we are not just testing the fidelity of the trunk system, but also like every small system that we see in the area. This is my study area. This is seismic volume from close to the Mississippi Depot Center. And there's a public data set available from USGS. And these are the late Miocene and the early Miocene extent of continental shelf edge. And as we can see that the seismic volume, the area of the seismic volume was always inbound from the shelf edge during both the times of our interest. There's a vertical section through the seismic volume from the study area. And the red, blue, and black lines are seismic reflectors, which can be thought about as stratigraphic contacts between in the area. The black curve is is a sea level curve reconstructed from Miller et al. 2005. And as we can see that the early quaternary signal, the sea level cycles are larger than the late Miocene sea level signals, and the the time periods are constrained by microfossil data available from USGS as well. The Salt Dome has been excluded from the interpretation, and I have interpreted a number of early quaternary and late Miocene channels from the seismic volume, which I'll talk about in depth. So a brief glimpse of the methods. So this is the seismic volume that we started our work with. Then I used an seismic attribute called the variance, which helps us in understanding how much does one voxel of the seismic volume differ from the neighboring voxels, which gives us an idea of where there's a change or an edge, like a fault or a channel margin. And that's how I ended up with these time slices and vertical sections, where I interpreted a number of channel bodies, and then used a Python code by Salt and Sylvester to calculate the distances between the widths of these channels, and also used thickness maps to calculate the depth and thickness of channels interpreted in the vertical section. There's an example from the quaternary and the Miocene section from seismic, and these are some of the interpreted sections that you see, interpreted channels that you see here. In total, I interpreted around close to 500 channels in early quaternary and close to more than 400 channels in late Miocene. This brings us to our results. So here we compare the channel body widths and thickness between quaternary and Miocene. Quaternary are the circles and Miocene are the crosses. And I also basically binned the channel widths using Gibling's database to see what kind of channel bodies could these widths signify. And we see that in case of quaternary, the major difference lies in the tails of the distribution, where the quaternary has like really wide and really thick channel bodies, which can be recognized as Paleo Valley fills or incised valleys. And this is an important point that I want to make, that the major difference lies in the tails of the distribution, and they look pretty similar in the majority of the area. So then we try to test whether the lower Miocene channel bodies really show autogenic signals or not. And we used the present day Mississippi channel width data and the thickness data which can be considered mostly autogenic. And we use that to compare to our early quaternary and late Miocene channel bodies. Here we see that, of course, the Mississippi channel is wider than most of our channels, but of course it's not as wide as the paleo values seen in the early quaternary, and it's not as thick as them as well. So they basically match better with the distribution of the lower late Miocene data. Also, we see that the deepest channel bodies from early quaternary show lower width to depth ratio, as can be seen here. Hence, these can be considered to be allogenic as well, or influenced by RSL. We also had well data. We had 6 wells from the Miocene and 1 well from quaternary well log data, and I created sand shale, calculated sand shale percentages from these. And here we see this is a map showing the spread of the wells that we have. And these are the percentages of late Miocene sand to shale proportion from the wells. But as I mentioned earlier, we only have 1 early quaternary well data, and so which does not really vary that much from the distribution of the ones seen from the late Miocene. And so we cannot conclusively say anything about using the sand shale proportion between the late Miocene and the early quaternary about how this affects, this changes due to RSL signals. One thing that I would like to bring up is the Miocene strata is composed of about 38% sand, which is quite similar to sand fractions calculated by Armstrong 2012. So this brings us to the discussion and conclusions, and the most important and one of the important slides of my talk. So this is an 8-star T-star plot, as I had shown earlier, and the calculations of 8-star and T-star are shown here. And in this plot, for every channel body, we calculated an 8-star and T-star value for early quaternary and late Miocene. And so here, the smaller channels are present up here. And as we go closer to the origin, we find the lower channels. We find the larger channels. And we see that almost all quaternary channels should have preserved RSL signals, whereas the late Miocene channel, about 40% of them do not preserve any RSL signal. And of course, 8-star and T-star are less than 1 in this case, and this is a shedding regime. Now, the one thing that I wanted to make it clear was, if there's a channel somewhere here for early quaternary, even it was definitely tucked by RSL. And when it was tucked by RSL, it would just become a deeper channel, but it would still be in the autogenic regime and would not immediately be in the shedding regime. However, for a late Miocene channel, if it was somewhere here and it was tucked by RSL changes, it would move to the shedding regime and would not preserve the RSL signal. So this brings us to the conclusion that our field testing of the signal shedding theory proves correct. And also, it's mostly the larger channels, the RSL signals, cycles tugging at them, that sets the fidelity of the basin, because those are the ones that will actually move into the shedding regime or out of the shedding regime effectively to show up in the stratigraphy. The other thing that I wanted to make sure was that the slope of this H-star T-star plot, it depends on the depth of the channel, the amplitude and period of RSL, and the long-term sedimentation rate. Thank you so much. And I look forward to answering all your questions at the session. Thanks. And thanks to Zoltan and David as well for all the help.